Okay, so here are some additional examples of static equilibrium problems involving torque. In this first one here, we have a lightweight rigid wire suspended from a rigid point on the overhead. We want to calculate the distance from the suspension line to the center of the right sphere. So to begin this, we have to recognize the conditions for this static equilibrium are that the sum of forces and the sum of torques must be zero. So we're going to start with drawing two pictures. The first will be a free body diagram of the forces on this system, and the second will be a diagram showing the torques. So let's look first at the drawing of the forces on here. We have a weight 1 on the left-hand sphere, we have weight 2 on the right-hand sphere, and we have a tension in this cord. So what our free body diagram shows us is that the tension would equal the weight of the two objects. So our first condition, net force equaling 0, is met. So now we need to look at our second diagram. Both of the forces on the spheres result in a torque. And since these torques are at 90 degrees to the lever arm, the entire force contributes to that torque. Now, if these things were to suddenly be able to rotate, okay, so if the left-hand sphere were to disappear, we have to think about the direction that this thing would rotate and where it would rotate. So it's going to rotate around the point where the cords are attached, right there. Okay, so we, in our torque diagram, show that point right there. That's our center point. So if the left-hand sphere were to suddenly disappear, okay, the torque on the right-hand sphere would cause this thing to rotate in this clockwise direction. If the right-hand sphere were to suddenly disappear, the torque on the left-hand sphere would cause this thing to rotate counterclockwise. Okay, so what that tells us then is that the torque on that left-hand sphere, because it would cause a counterclockwise rotation, is going to be a positive torque, while the torque on the other sphere that would cause a clockwise rotation is a negative torque. Okay, so now because we are in static equilibrium here, our torques must also be zero. Okay, so that's where we can begin with solving this problem, is by saying that our net torque is equal to 0. And because our expression for torque is Rf sine theta, we can plug those in, paying attention to our positive torque and our negative torque. And because our forces are due to the weights of the two spheres, we can plug in weight here. And finally, because our weights are acting at 90-degree angle to our lever arm, then the sine of 90 is 1, and we can get rid of that. So when we substitute in all of our values and solve, we end up with R2 equals 0.113 meters, or 11.3 centimeters. So let's take a look at this example here. We've got a teeter-totter in equilibrium. The block on the left has a weight of 625 newtons. The beam itself has a weight of 32.5 newtons. We want to know the mass of the block, this block here. This part right here is the fulcrum, the point about which this would rotate. So when we go to take a look at the forces on this, because it's in static equilibrium, we know that the net force on it must equal 0. So we'd have a weight at one end, a weight at the other, the weight of the board, and normal forces acting on each of those masses. Our other condition for static equilibrium then is that there's also no net torque. So when we look at this, our point right here at the fulcrum is the point about which this would rotate. And we have two torques that act. Now, even though the weight of the beam is high, its weight acts at the center of gravity, so there's no effect on the torque. So the weight of the beam acts right at the same point that it would rotate, so that weight of the beam does not act as it does not provide a torque at all. Torque 1 would cause this beam to rotate in a counterclockwise way, and torque 2 would cause this beam to rotate in a clockwise way. Okay? So if we have a counterclockwise torque, that's considered a positive torque. Clockwise torque would be considered a negative torque. So in our example here, our torque 2 is negative, torque 1 is positive. So when we go to work the problem out, our net torque on it is 0. Torque 1 is a positive torque, torque 2 is a negative torque. Both act at 90 degrees to our beam, so our lever arm, they act at 90 degrees. And the force is provided by the weight of each of those blocks. So when we add in our values, we end up with this, where we have a mass of 21.3 kilograms on the right-hand side over here. In our final example, we're going to look at a 250 Newton ladder that's 10 meters long, resting against a frictionless wall at an angle of 58 degrees. Now this ladder is set so that it just keeps from slipping, so we're right at that threshold point of friction on the floor. Okay, so we want to know what the forces are acting on the bottom of the ladder and what is the coefficient of friction at the bottom of the ladder with the ground. In order for this to be in static equilibrium, of course, we know that our net force and our net torque must both be 0. So we're going to start by drawing an elongated free body diagram showing the ladder and all of the forces acting on the ladder. So here we show that we have the weight of the ladder as WL. We have the friction force acting at the bottom of the ladder. We have F1, which is the force of the floor on the ladder, and F2, which is the force of the wall on the ladder. Now both F1 and F2 are normal forces from the surfaces that contact the ladder. We're just calling them F1 and F2 for simplicity right now. Now because this is a static equilibrium situation and we know that the net force and net torque are both 0, we can analyze the situation by looking at forces and at torques. If we start by looking at the forces on the ladder, we're going to look first in the y direction. Now when we're analyzing for forces in a problem like this, we can assume the object to be like a point mass, just like we've done with other objects, and look at forces in the x direction and the y direction separately. If we start with the y direction, we see that we have F1 positive in the positive direction when we have the weight of the ladder in the negative direction. So what that means is F1, the normal force then from the floor, is going to be equal to the weight of the ladder. We're told that the ladder is 250 newtons, so F1 is 250 newtons. So let's take a look then in the x direction. In the x direction, looking at forces, we have F2 from the wall, and we have friction from the floor. Friction in the negative direction, telling us then that F2 is going to be equal to the friction, but we don't have any other information about that, which we can't go any further analyzing this with forces. So we have to go and look at torques. So what we want to do here is start by, just like we start by drawing a free body diagram for forces, we want to do the same kind of thing when we start looking at torques. Okay, we're going to start with a diagram detailing the torques on this object. Okay, so here's our ladder, and we choose a pivot point at the base of the ladder here. So that's the point about which this would rotate. There's never any torque at that pivot point, so the forces at the base of the ladder, that F1 and that friction, are not going to provide a torque at all. Instead, what we've got here then is we've got a torque that is provided by the y component of the weight of the ladder, and we've got a torque that's provided by the y component of the force from the wall on the ladder. And as we look at this geometrically, we can see that we've got a 58-degree angle here, so we're going to have a 58-degree angle here and here as well. So what's really kind of important to get from this at this point is that these torques are provided by the components of the forces that act at these positions. Now torque 2 on here would cause this ladder to rotate this direction. So they would be rotating clockwise from torque 2. Torque 1 would cause the ladder to rotate counterclockwise. Okay? So there's where we can decide what our positive and negative torques are. So we see that torque 1 is going to be our positive torque, torque 2 will be our negative torque, and so when we go and sum up our torques, this is what we end up with. Now what we want to pay attention here to is where are the forces that result in these torques. For torque 1, that force is the weight of the ladder. So we use cosine theta because that is the y component of that force, of the weight of the ladder. On force 2, the component of the force that is perpendicular to the ladder will give us sine theta in our torque expression. So that's something to really pay attention to once we start working with these torque static equilibrium problems, is that which trig function are we using to applies that torque. We have to remember that just because the formula sheet says RF sine theta does not mean we're always going to use sine. We can use cosine if that is the component that we're looking at. So now when we go to substitute in our values, we're going to get this right here, where we're then told that, we're solved for F2 over here, and we get a 78.1 newtons. But remember what we said back over here when we're analyzing our forces is that F2 is equal to that frictional force there. Therefore, our answer is a 78.1 newtons. So when we go to solve for part B then, we end up putting that 78.1 newtons in for a force of friction, and we get a coefficient of friction of 0.31. So those are 3 examples of static equilibrium involving torques. There's other examples that we can look at, and we can talk about those in class. See you then.